We're now going to prove two additional theorems about subsequences, and the first one will be kind of obvious. And this theorem will have the following statement. Suppose that the limit of the sequence Sn is equal to S, and then the limit, then any subsequence of Sn is going to converge to S. Okay, and here is the proof. Because the limit as n goes to infinity of Sn is equal to S, by definition of the limit, for any epsilon greater than 0, there exists capital N in R such that n bigger than capital N would imply that Sn minus S is less than epsilon. So I'm going to consider any subsequence S and K of Sn, and let K to be bigger than capital N. So a couple of lectures ago we proved that nk is always greater than k, right? Remember, because nk is a strictly increasing integer valued function of k, now k goes up by 1, right, by itself, and then nk should increase faster than k, because if we go along the sequence, right, then we list terms in order, as 1, as 2, as 3, as 4, etc. But if we go along a subsequence, each time we jump by more than 1, by the amount which is greater or equal than 1. So we move along a subsequence faster than we do move along a sequence. And so because nk is greater than k, then what we have is that nk is greater than k, and k is greater than n by our assumption. So nk is bigger than n. So nk is an index of the original sequence which is greater than n. And therefore, by what we know about the original sequence, right? So nk is in particular is bigger than n. That should imply that Snk minus S is less than epsilon. So therefore, what have we found? We found that for every epsilon greater than 0, there exists a capital N, such that if k is greater than capital N, then Snk minus S is less than epsilon. But because k is now our index for the subsequence, then that means that the subsequence converges to S just by the definition of a limit again. Right, so once again, our final result states for any epsilon greater than 0, there exists an n in R such that if k is bigger than capital N, Snk minus S is less than epsilon. So that means, in fact, let me write it like this. So therefore, the limit k goes to infinity of S and k must be equal to S. And we're done. Okay, so something that I'm not going to prove, but also you can think of the opposite situation when you say you know that any subsequence of your sequence goes to the same number. Right, so if that is true, what do we expect? We should expect again that the sequence will converge to that number. In fact, actually, I said I'm not going to prove it, but it's really easy to state what the proof is. And it is the following, that the sequence, original sequence, by itself, is also its own subsequence. So if all subsequences of a given sequence go to the same number, then that automatically implies that the sequence itself must go to the same number because the sequence is its proper subsequence. So this is kind of if and only if statement. If a sequence converges, then all of its subsequences go to the same number. And if all subsequences of a sequence go to the same number, then a sequence converges to that number. Okay, so then the next theorem is this. Given any sequence Sn, the sequence always contains a monotone subsequence. Okay, let's try to prove this. And in a proof, basically what I would like to do, I would like to distinguish between the two cases. I would like to distinguish between the case when I can prove that the sequence contains an increasing subsequence and a case when the sequence contains a decreasing subsequence. It does not mean that both might not be true. The sequence may have both increasing and decreasing subsequences. But for this theorem, I only need to show that there exists one of such subsequences, whether monotone increasing or monotone decreasing. So I'm going to consider the two cases. Case number one, we're going to say that the term Sn, let's say 0, is dominant if element of a subsequence is dominant if Sn0 is going to be greater or equal than Sn, and this should be true for any n greater than n0. So Sn0 basically is dominant as long as it is larger than greater or equal than any term that follows. So then I'm going to assume that Sn contains infinitely many dominant terms. Now, that doesn't mean that all terms necessarily are dominant. For example, if I have a sequence -1 to the n, right, then -1 to the n will have terms -1, 1, -1, 1, -1, 1, etc. So which terms here are going to be dominant? -1 is not dominant because it is not greater than the terms, greater or equal than terms that succeeded. But 1 is dominant because 1 is going to be greater or equal than anybody else that follows. Similar, -1, next -1 is not dominant, 1 is dominant, 1 is dominant. So this would be an example of a sequence which contains infinitely many dominant terms. All right, so then I'm going to consider now a subsequence that consists of all dominant terms. So this subsequence is going to be labeled as SNK. And now what I see here, for example, in this sequence on the screen, well, what I see is that the subsequence of dominant terms will consist of 1, 1, 1, etc. Let's try -1 to the n divided by n. What are the dominant terms here? So the first term is -1, second is 1/2, -1/3, 1/4, and so on. So clearly -1 again is not dominant, but 1/2 is, so is 1/4. So every even term here is a dominant term. So 1/2 is dominant, 1/4 is dominant, 1/6 is dominant, and so on. So that would be a sequence of subsequence of dominant terms in this case. Maybe 1 over n squared. This is 1, 1/4, 1/9, 1/16. This sequence is decreasing, right? And because it's decreasing, then each term dominates everybody who is beyond it. So then in this case, every single term of a sequence is going to be dominant. So the subsequence of dominant terms is basically the entire sequence itself. All right. So then if I look at this sequence, it has a property. If I take a first dominant term, Sn1, and then I consider the next term, Sn2, Sn1 dominates everybody who follows, but Sn2 follows Sn1, so there is a greater or equal sign between the two because of the dominancy of Sn1. Likewise, Sn2 is dominant, so it should dominate the next dominant term, Sn3, same thing, Sn4, etc., greater or equal than Snk minus 1. This is greater or equal than Snk. right? And so then the conclusion is that the subsequence of dominant terms is decreasing. So it's monotone, and so then I'm done in this case. Now, what I'm saying is actually visible here, right? Ones are sort of trivially going down. They're not changing. One is greater or equal than one. In this case, in the second case, I have a sequence which is strictly going down, 1/2, 1/4, 1/6. And the same thing here, that the sequence of dominant terms, which are all terms in this case, also goes down. So in the case one, the conclusion is pretty easy, right? As long as I have infinitely many dominant terms, then a subsequence of dominant terms must be decreasing. Okay, so then we'll look at number two. What's the alternative to having infinitely many dominant terms? Alternative is that there are finitely many dominant terms. So now suppose that Sn has finitely many dominant terms. And if it has finitely many dominant terms, that means that I should be able to find the dominant term with the largest index. And if I find the dominant term largest index, with the largest index, and beyond that index, in the tail of my sequence, I don't have any dominant terms at all. So that means that there exists an index n1 such that there are no dominant terms in the tail or just when n is greater or equal than n1. Okay? Okay, so therefore Sn1 is not dominant. What does it mean? If Sn1 is not dominant, that means that there exists n2 greater than n1 such that Sn2 is going to be strictly greater than Sn1, right? Because if this was not the case, if such n2 would not exist, then that means that Sn1 is dominant, and so therefore that's a contradiction. So because it's not dominant, I can find the term further away in the tail of a sequence, which will be larger than Sn1. Okay, I can repeat this. Sn2 is also not dominant. All right, because all dominant terms were left in the beginning of the sequence. And so because it's not dominant, then there exists another index, n3 greater than n2, such that Sn3 is going to be strictly greater than Sn2. And so therefore, if I proceed by induction. I'm not going to write this down, but induction is clear here, right? If I take a term S and K, I should always be able to find, S and K is not going to be dominant, so I should be able to find S and K plus 1, which is going to be bigger. So by induction, we construct a subsequence S and K such that S and K is strictly increasing, right? Because each next S and K that I'm choosing is going to be larger than the previous one. And that's the proof. All right, and then next time we're going to prove to put these theorems to use in proving more theorems.